So again, this is section 4.9, Antiderivatives of James Stewart's Early Transcendentals Calculus book. This is applications of the derivatives, and in the last section we went over the general idea of finding antiderivatives, or the general antiderivative plus c. And so this one, we are going to, in this segment, we're going to cover the initial value problem. So in finding a general antiderivative, we are finding a family of functions whose derivative is equal to the function that we are given. And in this initial value problem question or situation, we're going to be given a specific set of criteria for our big antiderivative that will allow us to find a specific value of c. So let's take a look at this example here, example 2 from our worksheet. And it says find the antiderivative big f of x of our little f of x. So we're finding what function has derivative equal to this function. And we are given a specific criteria that big f of 1/2 is equal to 1. This is what we call the initial value. And it tells us that when x is equal to 1/2, big f of x is equal to 1. And we will use this to find a specific value of c. Or what they call a particular value of c. So we're finding the one graph in the family of antiderivative functions that passes through that particular point. Okay, so let's take a look at just finding the general antiderivative. So step 1 is let's find the antiderivative of f of x dx, and we use that notation of the integral with respect to the variable that we are finding the antiderivative with respect to. And our function here is 2 minus 1 over the square root of 1 minus x squared dx. And we know from the previous section, just like the derivative of a sum or difference is the difference or sum of the derivatives, same is for antiderivatives. So we can say that this is equal to 2 times dx minus the integral or the antiderivative of 1 minus the square root of 1 minus x squared dx. Okay. In looking at a basic table of with the very first term of what function has derivative equal to 2, we definitely, it's very easy for us to see that that is equal to 2x. If you consult a basic table of integrals, or even the basic table of derivatives, what function has derivative equal to 1 over the square root of 1 minus x squared, you can consult those tables, and we find that this is equal to the inverse sign of x. Now we don't want to forget to add our general solution plus c. So this entire expression here is our general solution, or general antiderivative. So just like in the case when we are finding instant rates of change, we first find the derivative and then we take our given values and we substitute it into our derivative to find a specific instant rate of change. We're doing the same thing here. We will take our initial value. Once we find our general antiderivative, we're going to use our initial value to find a particular value of c. So we take our initial values of big F of 1/2 is going to equal 1. So recall that means when x is equal to 1/2, big F of x is equal to 1. And so we're going to substitute 1 in the big F of x, and we're going to substitute 1/2 where x appears, and we're going to solve for c. So when 1 here is equal to 2 times 1/2 minus the inverse sine of 1/2 plus c. We know that what function or what inverse sine inputs a trig ratio and outputs an angle between negative pi over 2 and pi over 2. And so the inverse sine of 1/2, right? Inverse sine of 1/2 is going to give us a theta, where theta here is between pi over 2 and negative pi over 2. And so if I just drew a particular triangle with our theta, our sine is opposite over hypotenuse. And so I can quickly see that in this range, theta here is equal to pi over 6. So in looking at this, I have 1 equal to 2 times 1/2 is 1. Inverse sine of 1/2 is pi over 6. And so I can tell here that pi over 6 is equal to c. So my particular solution which is the solution to the initial value problem, is big F of x is going to equal 2x minus inverse sine of x. And instead of using plus c, we use plus pi over 6. And that's going to be our answer. Okay. So we're going to jump ahead, and yes, this is in general an introduction to differential equations. This is the very first thing that you learn in a differential equations course, and that separability of functions, or the initial value function. So what is a differential equation? It is an equation. It's a statement with an equal sign. And it also, a differential equation is an equation that contains a derivative and its functions. In this particular section, we only involve ourselves with the first derivative. And so the initial value problem is your first introduction to differential equations, where you are given like an f prime of x equal to a function, and then you're given an initial value. So we can find the solution to that differential equation, and the solution to a differential equation is the function itself. So remember, a differential equation is an equation that involves the derivatives of a function and the function itself, or maybe not. But the solution to the differential equation involves an arbitrary, the general solution, but the real solution to is a function, right? And so your general solution is going to be your family of functions, but if we are given an initial value, we can find a particular solution to the differential equation. So let's take a look at this example, and it says solve the initial value problem given that the derivative f prime of x is equal to e to the x plus x squared minus 4, and we have the initial value of f of 0 is equal to 2. So that means when x is equal to 0, f of 0 is equal to 2, or your y is equal to 2. Good. So let's take a look, and just in looking at the notation, f prime of x is equal to e to the x plus x squared minus 4. We can replace, this is going to give you some motivation for future sections. What does f prime of x in the Leibniz notation give you? That's a dy dx equal to e to the x plus x squared minus 4. We can separate our variables x and y. We can look at dy as a differential, dx as a differential. We can multiply on both sides by dx and get dy equal to e to the x plus x squared minus 4. And multiplying on both sides, the dx goes away on the left-hand side and it appears on the right-hand side. And now we can integrate both sides. And when we integrate both sides, what function has derivative equal to 1? Because 1 times dy. Y does. And if we integrate on term by term, remember this is going to be e to the x dx plus x squared dx minus the integral of 4 dx. And what function has derivative equal to e to the x? E to the x does. We're integrating with respect to x, and we have x to a number, so we can use our power rule. So we can use x to the 2 plus 1 over 2 plus 1. And what function has derivative equal to 4? 4x does, right? But we don't want to forget to add our plus c. We get our general solution here. And just simplifying that general solution, we get e to the x plus x cubed over 3 minus 4x plus c. And that's our general solution. We now introduce our initial values to find c. And so we have when x is equal to 0, f of x, which is y, is equal to 2. So we're going to substitute the value of 2 here, and we're going to substitute the value of 0 everywhere in the expression and solve for c. So we get 2 equal to e to the 0 plus 0 cubed over 3 minus 4 times 0 plus c. We get 2e to the 0 is 1. We get 0 minus 0 plus c. And I find here that solving for c, we get c equal to 1. So our particular solution is the general solution, but we replace the plus c because that's the arbitrary constant. It's the family of functions. The particular solution satisfies the initial value that we are given. It is the particular function that passes through that point. So we would get f of x. We still get e to the x. We still get x cubed over 3. We get minus 4x, but now our c we determined was 1, so it's going to be plus 1. And that is our answer. Okay. Does this example contain, in this next example, does this contain a particular value? Does it contain an initial value? No. So there are no initial values here, but we're given a second derivative, right? And remember in our last section, we only have the power rule. We don't have in our basic table of antiderivatives or our basic table of integrals, we don't have radicals in them, but we can still change them to exponential form, right? And we also do know that we have multiple derivatives or higher order derivatives, but it doesn't mean that we can't do higher order antiderivatives. We can get back to the original f from a second derivative. We just might have two arbitrary constants And so when we have two arbitrary constants, we can use different letters of the alphabet in capital letter form, or we can use subscripts like C1, C2. I tend to prefer the C1, C2, so we will go there. Okay. So we do, just to be clear, the integral of f double prime is going to be your first derivative plus C1, and your integral of f prime plus C1 dx is going to be your f plus C1x plus C2, right? That's basically where we are going with this, right? And finding what function has derivative equal to. We know with the second derivative, we're finding what function, which is the first derivative, is going to have that equal to. So let's start with our second derivative. And that's going to be the fifth root of x cubed plus 2 over the fifth root of x dx. We know that the integral, or the antiderivative of a sum, is the sum of the antiderivatives. So we know that this is going to equal the fifth root of x cubed dx plus the integral of 2 times the fifth root of x dx. I am now going to change them into exponential form so I can use the power rule. And I see that whatever our index is our denominator. So this is going to be x to the 3/5 dx. We have a negative exponent, so this is going to be 2 times x to the minus 1/5 dx. And so now I'm going to integrate term by term. And this is going to be x to the 3/5 plus 1 over 3/5 plus 1 plus 2 times x to the minus 1/5 plus 1 divided by minus 1/5 plus 1. And we don't want to forget our plus C1, right? I see that 3/5 plus 1 is 1 3/5, and 1 3/5 is going to be 8/5. And division by a fraction is multiplication by the reciprocal. And so I'm going to get here that this is going to be 5/8 times x to the 8/5. Same here, negative 1/5 plus 1 is going to be 4/5. And division by a fraction is multiplication by the reciprocal. And so this is going to be division by 4/5 is times 5/4, and we're going to get times x to the 4/5. And don't forget the plus C1. Just cleaning things up, I can cancel the 2 with this 4 to leave a 2. And so we're going to get that our f prime of x is going to be 5/8 x to the 8/5 plus 5/2 x to the 4/5, and we have plus C1. Now I'm going to integrate f prime of x dx. That's going to be the integral of 5/8 x to the 8/5 dx, and the integral of a sum is the sum of the integrals. And we have plus C1 dx. Remember, the integral of a constant is the constant times that integral. And so we're going to still get that this is 5/8 and x to the 8/5. Remember, we add 1 to the exponent and we divide by that same exponent. Plus, we have 5/2, and we are going to add 1 to the exponent, and we're going to divide by that exponent. The antiderivative of a constant is going to be that constant times x, because what's the derivative of c sub 1 times x? It's just going to be c sub 1. But we now don't want to forget to add our plus c2, our second arbitrary constant. 8/5 plus 1 is going to be 13/5. And division by a fraction is multiplication by the reciprocal. And so we're going to get 5/8 times 5/13. Right? And 8/5 plus 1 is still 13/5. So we're still going to get x to the 13/5. 4/5 plus 1 is 1 4/5. And 1 4/5 is 9/5. Division by a fraction is multiplication by the reciprocal. And so division by 9/5 is multiplication by 5/9. And we still have x to the 4/5 plus 1, which is 9/5. We still have plus c1x. And then we also still have plus c2. Simplifying that completely, we end up with, and this is our f of x, and so our final answer, f of x here, is going to be 25 over 8 times 13, I believe is 104, times x to the 13/5, plus 5 times 5 is 25, 2 times 9 is 18, times x to the 9/5, and we still have plus c sub 1 times x plus c sub 2. And that is going to be our answer. And how can you check? You want to check by find f double prime of x and confirm it is where we started. Okay. So the very final one that we're going to do is we're going to do a motion problem, which you will find many applications for. Galileo once long ago discovered the acceleration constant due to gravity, 9.8 meters per second squared, or 32 feet per second squared in a different units of measurement. Well, if we start with acceleration, we can take the antiderivative of acceleration to get to the velocity function. And from velocity, we can take the antiderivative to get to the position function. So we can actually get to an equation that models where the object is at time t. So you can see this application has great applications in the real world situation. So let's take a look at our rectangular motion or rectilinear motion. So remember, position is s of t, velocity is s prime of t, and acceleration is s double prime of t. And so we can see that the antiderivative of acceleration is going to be our velocity of t plus c, and our integration of velocity is going to be our position plus c. So in a lot of our rectilinear motion problems, you might have two particular initial values so that you can find the exact position of the object at time t. So let's take a look at this example here. Suppose an object moves along a straight line with an acceleration of a of t equal to 4 cosine t minus sine t meters per second squared. where the initial velocity, so this tells me when t is equal to 0, v of t is equal to 1. And the initial position, when t is equal to pi over 2, s of t is equal to 4. Good? Those are our initial values. So it says find the position and velocity functions, including units, and then determine the position and velocity at t equal to pi seconds. Okay, that's an S. All right, so we begin with a of t equal to 4 cosine t minus sine t meters per second squared. And we're going to take the antiderivative to find the velocity. All right, so if we take our antiderivative, we're going to get our initial velocity plus c. So we're going to take the function for cosine t minus sine t, and we can integrate that term by term to get our v of t. So our v of t is going to be, what function has derivative equal to 4 cosine t? 4 sine t does. What function has derivative equal to sine t? Negative cosine does, right? Because minus cosine, the derivative of minus cosine is minus sine, and so minus sine is going to be sine. So we get that. Plus c. Cleaning things up, we get 4 sine t plus cosine t equal to c. And you can check by taking the derivative there to see that we get the original acceleration. We want to bring in our initial value for velocity. And we have that v of 0 is equal to 1. So when t is equal to 0, v of t is equal to 1. So we're going to substitute 1 for where v of t is, and we're going to substitute 0 where t is, and we're going to solve for c. So here I go. 1 is going to equal 4 of sine 0 plus cosine of 0, and we still have plus c. We have 1, sine of 0 is 0, so this is going to be 0. Cosine 0 is 1. And so I see here that 0 is equal to c. So I can determine then that v of t, our velocity, is going to just be 4 sine t plus cosine t. So that is our function for velocity of our object. Next up, we want to find our position. Our s of t is going to be the antiderivative of v of t dt. So this is going to equal 4 sine t plus cosine t dt. Taking that antiderivative, we're going to get, what function has derivative equal to sine t? Negative cosine t, right? Remember, the derivative of minus cosine is minus sine, which gives us sine. So this is going to give us 4 times minus cosine t. What derivative, or what function has derivative equal to cosine t? Sine t does. And we don't want to forget to add our plus c. So we are getting minus 4 cosine t plus sine t plus c is our position function. We want to use our initial values of sine of pi over 2 is equal to 4. So that tells us when t is equal to pi over 2, s of t is equal to 4. So we're going to substitute 4 where s of t is, and we're going to substitute pi over 2 where t is, and we're going to solve for c. So we get 4 is equal to minus 4 cosine of pi over 2 plus sine of pi over 2 plus c. Cosine of pi over 2 is 0. Sine of pi over 2 is 1. And so in solving for c here, I get 3. So my position function, the particular one that satisfies the initial values, is going to be minus 4 cosine t plus sine t, and we're going to add plus 3 and not just plus c. We don't want to forget to answer the questions that they asked. It says, then determine the position and the velocity at t equal to pi seconds. So at t equal to pi seconds, also velocity, if we are given meters per second squared, velocity is going to be in meters per second. Position is going to be the distance at time t, and that's going to be in meters. So at t equal to pi seconds, v of pi is going to be 4 sine pi plus cosine pi, and that's going to be 4 times 0 plus negative 1, and that's going to be minus 1 meters per second. So we can see that we are moving backwards. Now, s of pi is going to be minus 4 cosine pi plus sine pi plus 3. That's going to be minus 4 times minus 1 plus 0 plus 3, and that's going to be 7 meters. And that is where the object is relative to its initial position. Is going to be 7 meters forward. And that's going to conclude this video for today, and I might include another one on initial values or motion. Take care. Have a great day. I will see you in the next video.